Solve each polynomial by factoring. In these examples, we see that our variables are raised to higher exponents than just the second power. But we can still factor by thinking about taking out the greatest common factor. For example A, the greatest common factor is y. So I'll factor a y out of each of the terms that is listed there. And then what's left in parentheses is a difference of squares. The first term, 4y squared, its square root is 2y. And then my second term, 9, its square root is 3. When I have a difference of squares, I have a plus in the middle of one of those terms and a minus in the middle of the other term. So here's my factored version. I can now use the zero product principle to separate this into three different equations. So we have that either y is equal to 0 or 2y plus 3 is equal to 0 or 2y minus 3 is equal to 0. For the first equation here, we're already done solving that. For the second one, let's subtract 3 from both sides. So then 2y equals negative 3, and we're getting that y is equal to negative 3 halves. That's a second solution. And then for the third equation, let's add 3 to both sides. So 2y is equal to 3. And then if we divide both sides by 2, we'll get that y is equal to 3 halves. So in this case, we're getting 3 solutions, which kind of matches up with the 3 that we saw as the exponent originally. Let's look at the next example. I have variables on both sides of the equation here. So what I want to do is get everything onto one side and 0 on the other in anticipation of using that zero principle. So let's start by subtracting the 14x cubed so that it moves over to the left. And then it looks like I can factor out a 2x cubed from both of the terms there. I'll be left with x squared minus 7. Oh, just minus 7. Okay, let's fix this. And then I can separate this into two equations with either 2x cubed equaling 0 or x squared minus 7 equaling 0. On the left-hand side, if I divide both sides by 2, zero over 2 is just 0. X cubed is equal to 0, and the cube root of 0 is 0. So x is just equal to 0 for this first equation. For the second one, I have that x squared is equal to 7, and then if I take the square root of both sides, I have to remember to have a plus or a minus in front of the 7 because we're solving an equation. So here we're getting two answers. We're getting that x is equal to positive root 7 or x is equal to negative root 7. Now notice that in this example we're ending up with only 3 answers. Even though the exponent was raised to the 5th power, the exponent that's listed there is the highest number of real solutions that we're getting. The 3 that we're getting here are real numbers, and so that means that there are 2 additional numbers that are complex or imaginary numbers. We don't need to worry about that too much right now, but I just wanted to point out that that exponent is the most number of solutions that we would see. All right, for this next set of problems, we're going to solve polynomials by grouping. We saw factoring by grouping when we were factoring trinomials, polynomials with 3 terms that had a coefficient in front of the leading term. We also use factor by grouping when we have 4 terms in a polynomial. So the idea is to group the first 2 terms together, and then group the second 2 terms together, and then factor out the greatest common factor between them. So for the first 2 terms, they both have a 3x squared in common. So I'll put 3x squared on the outside, and I'll be left with x minus 2. Now, when we did factor by grouping, we said that the x minus 2, or the item that's in the parentheses, needs to match with the first one. I want this to match with this if the grouping is going to work correctly. So now I have to figure what goes in this space. If I pull out here a negative 27, let's see what happens. This will give me the negative 27x. And then negative 27 times negative 2, that'll give me the positive 54. So that looks like it's what I'm looking for. These 2 items are being grouped together, x minus 2. And then these 2 items are being grouped together, 3x squared minus 27. And this whole thing is equal to 0. So now what I'll do is I'll split this up into 2 separate equations. 3x squared minus 27 is equal to 0, or x minus 2 is equal to 0. For the first one, let's move that 27 to the right, add 27 to both sides. Divide both sides by 3. That should be a 2 there. And then we'll take the square root of both sides. And when we do, we'll have a plus or a minus. So we get that x is equal to plus or minus 3. And then the equation over on the right here is just going to be x equals 2. So here are the 3 solutions. X is plus or minus 3, or x is equal to 2. For example B, it looks like I forgot to write an equals 0 here, so we'll just write that there. All right, again, we're going to factor by grouping. I'll group the first 2 terms together and then the second 2 terms together. For the first 2, it looks like I can bring an m squared out to the front, and I'm left with m plus 1. I want the what's inside the parentheses to match, and I want to ask myself what would have been factored out of these 2 to end up with an m plus 1. And it looks like it would be minus 1. This will give me minus m, this will give me minus 1, so that's going to work. All right, putting this and this together, I get m squared minus 1, and that's multiplied by m plus 1. M squared minus 1 is a difference of squares. It's m plus 1, m minus 1. So it looks like I have one of these terms that is repeated. So I'm going to have that either m plus 1 is equal to 0 or m minus 1 is equal to 0. I don't need to repeat the m plus 1 again because it'll give me the same answer, right? M is equal to negative 1 or m is equal to positive 1. When we have a solution that's repeating, it actually changes what's happening with the graph. What ends up happening with the graph is that we know that we have x-intercepts at negative 1 and at positive 1. And the x-intercept that showed up at negative 1, that one is repeated. And so what ends up happening on the graph is that at that x-intercept, the graph actually sits right on the x-axis like this, and then the other one passes through the axis. This is something we'll talk about in some later sections, but I just wanted to point out that the significance of that repeated x-intercept does impact the overall graph.